Good evening, everyone, and welcome to the third edition of the Vacuum Transport Seminar in spring 2021. We would like to welcome you, the guests, but also our partner institutions. So we're still the hosts and the co-founders are EuroTube and Swissloop, and our partners are the University of Applied Science, Emden, Leer, and the University of Oldenburg, the Institute of Hyperloop Technology, as well as the Technical University of Munich and TUM Hyperloop. All the organizations will give a short talk and an insight into their field of research in the Hyperloop area. We start off by Swissloop and EuroTube Foundation, and afterwards by the University of Applied Sciences in Leer and the Technical University of Munich. Then we go ahead by the goal of the seminar, the seminar schedule, and our Slido tool. So a short insight about Swissloop. We're the university team of ETH Zurich. We're a student team, a student from ETH, but also from other Swiss universities. We do research on Hyperloop prototypes, so on pods. We compete in international competitions and events. So we participated in the SpaceX competition for 3 times. And this year we compete in the European Hyperloop Week. We're in close contact to sponsors from the industry, but the whole engineering and development we do in-house by the students. We're a team of roughly 30 students and are also a project of the Department of Mechanical Engineering, a so-called focus project. Here we give a short overview of Swissloop's history. So it was founded in 2016, and ever since, Swissloop constructed and designed 4 different pods, and we're currently in the 5th year designing the newest pod. And here on the right you can see the current team. Here a short insight from the pods we developed so far. So we started off in 2016 and 17 with a cold gas propulsion system. Then in 17-18 with a linear with a electric motor. Then 18-19 with a linear induction motor. 19-20 also linear induction motor, and this year also going to be a linear induction motor. Okay, then I hand over to Fabio from the EuroTube Foundation.
Sure, thanks very much, Natalie, for the introduction from your side. Quickly to my person, Fabio Dubois, heading the technology developments at the EuroTube Foundation, also here in Zurich, currently also in the home office. I guess all of you are currently in the home office, enjoying and doing your work at home. So yeah, who is EuroTube? We as a non-profit research organization and incubator for sustainable vacuum transport technologies, we have 3 pillars of activity. We are doing research and development of different vehicle and infrastructure technologies. We have an incubation and transfer activity where we look into first applications and spinning off certain technologies into the market. And of course, we are also part of the certification and regulation efforts here in Europe, but also in other areas, in order to accelerate sustainable transport in terms of vacuum transport, not only in the technology, but also in the political domains, and to make it a reality. And recently we were also accredited by the Swiss government as a research institute of national importance. And we were very glad to be supported by them also in the next coming years, and hopefully to grow the ecosystem around vacuum transport more, not only in Switzerland, but of course also on a European and even hopefully on a worldwide scale. So that's our mission. On the next slide, you see a mission and the roadmap, where we have on the left-hand side the academic research and commercial applications, like several of the other players and organizations now out there, and also, of course, the organizations that are part of this seminar. We are transferring a lot of knowledge that is already been gathered from academia into industry. And on this roadmap, we have several milestones. Some of them were already in our past. So the actual foundation of EuroTube back in 2017. And now we're looking into first demonstrator construction projects here in Zurich. So stay tuned to that. And hopefully we will also be opening the Alpha Tube test track in the mountainous region in Wallis. Maybe some of you know it from skiing or touring. That's the two big projects that we are working on with our partners from academia and industry. And on the next slide, you can see some impressions on what kind of research we do within our engineering teams with our research partners, Swiss, German, Italian. It's on the left-hand side on the infrastructure domains, for example, the shell systems, the entire power and energy systems provided on site, the vacuum assurance, of course, as a key element, but nonetheless also the vehicle systems, which have very much a dual kind of component to the trackside systems. To name a few, you see the compressors, you see the battery systems, but also the onboard propulsion. Yeah, I think that was already my last slide. I'm very much looking forward to kick off the third edition of the Vacuum Transport Seminar with all of you, with our new and old friends, and with you, of course, the audience, and of course, with all the students and the guest speakers that will bring in their expertise and their input talks. Really looking forward. And now I'm handing over to, I think it is Lucas. And that's maybe just as an overview and wrap-up slide, what the Alpha Tube should look like. Some specs, you can also have a look at it later in the video broadcast, which we'll put also on our new website, which is vacuumtransport.org. So now definitely to Lucas.
Thank you. Yeah, I just want to say there's one more slide for you. Thank you, Natalie. So we also started with the Hyperloop Pod competition team early on, and then decided to implement the Hyperloop into the curriculum. That's what you see there. That's where we started with the University of Applied Sciences in Leer and the University of Oldenburg. We started with bachelor and master's thesis, and now also have it in the curriculum, and we're very happy about that. And we are very much looking into this project of project-oriented learning and making this a reality here. With the Institute of Hyperloop Technology, then we also have the research and development of Hyperloop technology and applications. On the other side, we also have the European large-scale research and technology infrastructure that we are pursuing over there. So there's a combination of mobility and intermodal transportation, and then also system technology, levitation, and at the end, then integration and verification of those technologies. In order to pursue those, we also got a grant from the Ministry of Lower Saxony. And on the next slide, you will see our plans for the large-scale research infrastructure we're going to look at. We also have some impressive numbers there. So maybe some of the maglev test track in Laden, that's also in Lower Saxony here. We are looking into transforming that into a European large-scale Hyperloop research facility. Has a track length of 32 kilometers and a very large footprint, so it's very hard to acquire such an amount of land for quick development of a transportation system. So that's why we think that this facility is perfect for implementing a Hyperloop large-scale facility on a European basis. And then this facility will provide researchers and private sector all the necessary tools that they need. Already curves and everything that we loop on a European basis. On you will see the 3 steps that could be taken. So phase 1 will into the materials and tubes of the superstructure. Then phase 2 is already looking into integrating a linear track, and then also a switch into this old facility that we have there, which you can use most of the superstructure for the new development of Hyperloop then. And the third one is the construction and then the operation. of the whole infinity loop that you have there, and that's the long phase there that you see up there, and there, which is currently to the EU governments funding other research organizations. That's what you'll see on the next slide, the last slide for us. That's our projects that we are currently working on. We're working on networking, on consortium building, and generally on an open Hyperloop network with hubs and with a hub and line and satellites. All of this here you can see on the right. We're working on this large scale structure side of the Hyperloop development program, for example, on the roadmap for the European Hyperloop. The one on the bottom left, the Epicenter project, where you can see the intermodal Hyperloop and its impact on transportation and logistics just in general. And I think that's it for us.
Okay, I couldn't hear the last words, but I think it was a handover. So, hello everyone, my name is Leer. I'm the team lead at the TUM Hyperloop team, which is the Hyperloop team of the Technical University of Munich. I'm also really glad and thankful that we have the opportunity to take part in this seminar this year. So also a few words and a short introduction from our side. So we are TUM Hyperloop, and on the next slide you can see a bit of our history, because our team was also funded because of the SpaceX Hyperloop Pod competition in LA. So we started with the first competition in 2016 and competed in every single year afterwards. In the first competition, we were lucky enough to win with our huge proof of the concept pod. And all the years after, we tried to improve our concept and be a bit faster and compete in this competition. And this way, we were also successful enough to get the trophy for the fastest pod in every consecutive year in 17, 18, and 19 with our pods. But there were, of course, also other victories, not only the fastest speed, as we know from Swissloop and also other university teams. And before actually after the last competition, before it was announced by SpaceX that there won't be any competitions anymore, we were also thinking that there's actually more potential in Hyperloop than just taking part in this competition. That's why we decided to shift our focus more towards research and developing a full-scale system, which you can also see on the next slide. And actually, parallel to the last competition, we started to develop a small-scale ring, which I actually shown on the first slide. It was a small-scale tube, a concrete tube with a vacuum system and a functioning levitation and propulsion system. And that was our first step on this road towards a more research-based project in the TUM Hyperloop team. And the next steps you can also see on this slide. Right now we are working on a slide before actually. Right now we are working on. Could you please go back one slide? I was still on the roadmap. Yes, thank you. So right now we are working on a 24-meter segment demonstrator, which means that we are working on a full-scale segment of a tube and also a pod, which will be also a functional, magnetically levitated and propelled system. And afterwards, a year afterwards, we are looking into a more like a longer test track with 1,000 meters, and hopefully later in the future, at some point also 10+ kilometer reference track, where we can actually see the real potential and higher speed of a Hyperloop system. For this, of course, we're not completely alone. We get a huge support from the university, not only knowledge, but also academic support. And on the other side, we also get support from the industry, from the industrial partners, not only financially, but also, again, with the experience and knowledge. And finally, the Bavarian government is also trying to include us in the long-term transportation plans and future of Bavaria, which we're also really thankful for. And on the last slide, it's just a few words about how our team is structured. Currently, we have 4 main areas in our team. First of all, it's a technology development and demonstrator, where we are taking a look into this previously described full-scale track that we are developing. And the next part is the simulations and modeling, where we are taking a look into areas like aerodynamics, for example, that is really hard to actually test in reality. But of course, it's a crucial part of the whole system. There are also feasibility studies and route planning, where we are trying to figure out, considering all the costs and demand and all the factors that come from routes in Germany, for example, between Munich and Berlin. And we are trying to come up with possible routes that could be built in the future. And finally, there's a safety analysis, where we are developing a concept for life support system and also emergency systems. And concluding all this, I'm also really happy to be part of this. And I hope that this collaboration between the teams and institutions and companies is going to continue in the future, especially in Europe, because that's the only way how we can achieve the long-term goals of Hyperloop, building a Hyperloop system in Europe, because we will have to work together and bring it to a success. Thank you.
Thank you very much, Fabio, Lucas, and Levente, for giving an insight into your organizations. And yes, as Levente said, it's really important that we all collaborate and exchange, which basically is one of the goals of the seminar, to offer a platform where these interactions can take place and where we can all contribute. So, which brings us to the next slide, what the goal of the seminar is. So, we want to provide a platform that students can present their work from all these institutions, and also that experts can give input talks, and for that we can foster the exchanges. Then, as you could maybe already see, those are the dates that the seminars this semester will take place. It's last semester it was every second Monday, but this semester it's basically every Monday except of 2. So those are the Mondays on which it takes place. And also something new is the website. We have now a joint website for all the organizations, and it's vacuumtransport.org. On the website, you can also see, you can also find an archive from the previous seminars with YouTube links. Now, those of you who joined already last semester, we use slido.com for the exchange rounds. It's a website where you can enter your questions during the presentations, and at the end, we go through all the questions, and you can also upvote the questions if you see some that you like, and we can go through the questions that have the most upvotes. So it's already starting today. The website is slido.com, and the event code is VAC Transport Seminar. So keep that in mind. Then Swissloop and EuroTube also offer projects. So this is maybe more an information for the Swiss students, but basically also for international students. You can find it on the Swissloop website on swissloop.ch/research, where we have listed the current projects. So feel free to reach out to Fabio or me if you're looking for a thesis to conduct. So this was already it from the introduction. Thank you again, Fabio, Levente, and Lucas, for presenting your institutions and their organizations. And we now start into the seminar session. We have 2 talks today. And now I would like to hand over to the first talk, which is by Maurice Pizzocero. He's a master's student in mechanical engineering at ETH Zurich, and he talks about a compressor design and the fluid dynamics, or the CFD application investigated. So I now stop sharing and I hand over to you, Maurice. Thank you.
Thank you, Natalie. Thanks a lot. Let me share my screen. So thank you, Natalie, for the introduction. My name is Maurice Pizzocero. I'm a mechanical engineering student at the ETH of Zurich. And I just completed my master thesis, so today I will present a summary of my work. The thesis title, as you can read, is Study of Hyperloop Pod equipped with a compressor to overcome the Kantrowitz limit. So let's begin. Oh, this is Slido, as Natalie already mentioned, is for the questions. If you have questions at the end, just feel free to post them, and I will be glad to answer them. So here is the table of contents. I will start with the motivation and research objective of my work. And then I'll have a slide on the Kantrowitz limit, on what it is and why it can be problematic for Hyperloop in general. And then I will talk about the strategy and the CFD setup I use for the analysis. And my work is actually divided into two parts. First, I investigated what happens when this Kantrowitz limit is exceeded without a compressor, so for a pod without a compressor. And in a second step, I included a compressor in the analysis and look at what happens to the flow and also if we can get some benefit from it. And obviously at the end, the conclusions, limitations, and the outlook and the questions. So let's begin with the motivation and research objective. The goal of my thesis was to investigate the possibility of mounting a compressor in the front part of the pod. Why? Because a compressor was actually included in the original formulation present in the Hyperloop Alpha paper published by Elon Musk in 2013. And in their design, a compressor was used for two reasons. First was to generate compressed air for the air bearings, which is not or are not present in current designs. So this first problem does not concern us anymore, but the second one does. And it's namely overcoming the Kantrowitz limit. And in short, the Kantrowitz limit is the condition under which the flow around the pod chokes. And when this happens, the pressure accumulates in front of the pod, leading to an increase in drag and ultimately to an increase in the power required to propel the pod. So it should be avoided if possible. And a compressor, as you can see in this picture I took from the Alpha paper, mounted in the front part, can allow, or could in theory allow, more mass flow to flow through the pod, and therefore releasing part of this accumulated pressure in front. So I try to answer the following research questions. In the first part, what happens when the Kantrowitz limit is exceeded? And in a second step, can a compressor reduce this pressure accumulated in front? And can it reduce ultimately the total power consumption of the system? And also under which conditions should a compressor operate? So the Kantrowitz limit, we are basically considering the following situations. We have a pod of area A pod, which travels at Mach number MA1 in the tube area AT, and the flow gets squeezed in the bypass of the area ABP and accelerates to Mach number MABP. So if you do the mass conservation between tube and bypass, you get the following expression, which relates the two areas with the two speeds. And now if we define the blockage ratio as the ratio of the pod area over the tube area, and also if we set the Mach number in the bypass equals to 1, which is when the flow in the bypass is choked, we get the following equation. And we can actually plot this in this two-dimensional graph with the Mach number of the pod on the x-axis and the blockage ratio on the y-axis. And this blue line is this equation here, which is the Kantrowitz limit. So essentially, for all the conditions above this line, so for fast pods or high blockage ratios, the flow in the bypass chokes and the Kantrowitz limit is overcome. And so I focus on this region, or specifically in the second part of the analysis, I will focus on this region here. So concerning the strategy, I performed two-dimensional axisymmetric simulations because they're fast and they allow for, or they are suitable for a parameter study with the software developed by Siemens StarCCM Plus. And as I said, I distinguish between two parts. I first investigated the full parameter space, which I just showed you, without a compressor. And only in a second step, I include a compressor or a modeling of the compressor. I will get back to that in a second. and compare the power requirements. Why the power requirements? Because you need to consider the following key point. Essentially, a compressor is pointless or useless if its power requirement is higher than the gains due to the reduction in drag. As I said, the compressor is used to reduce this pressure accumulated in front, and therefore reduce the power that needs to be provided by the linear induction motor. However, the compressor itself uses some power, so it needs to use less power than what you gain, essentially. And I will get back to that later in this presentation, but this is really the key point of the analysis. So this slide is about the pod designs. As I said, I have two parts. So for the first part, it's a pod without a compressor, 2D axisymmetric, so very simple. Not much to say about it, except that the radius is variable, because as I said, I have varied the blockage ratio, and by that I mean I changed the pod size or pod radius. And for the second part, again, very simple shape, but this time the pod as a whole through it to allow for the compressed air to flow through, as in the picture I showed in one of the first slides. And essentially, I place the modeling of the compressor in this initial converging section. And also, again, the variable radius of the pod is here together with some constraints. And yeah. And this is the domain with the boundary conditions. So as I said, I changed the tube size, but sorry, the pod size is changed, but the tube size is fixed. So, or the domain size in this case is fixed. The length of the tube is 40 meters. And more importantly, the diameter is fixed of 2.2 meters. And also the pressure inside the tube is 0.1 atmospheres, so nearly evacuated. And I use the following boundary conditions. Mass flow is an inlet, outlet is a pressure outlet. This line here is the symmetry axis, or sorry, the axis of rotation, moving wall on top, and the pod is a fixed wall. And yeah. So let's move on to the results of the first part concerning what happens when the Kantrowitz limit is exceeded. And let's first focus on the flow structure. So essentially, the flow around the pod follows the same path as in a de Laval nozzle, which you see it here in this picture. So it gets squeezed from a larger area of the tube into a throat, which in our case is the bypass, and then gets expanded again. And so in a de Laval nozzle, the ratio of pressures upstream over downstream determines how the flow evolves through the nozzle, either remaining subsonic or accelerating to supersonic in the diverging part, and then with a normal shock somewhere in this part, or remaining supersonic overexpanded. And so in our case, the pressure accumulated in front leads to the formation of one of those three cases. And let's consider three sample cases or three sample solutions. So again, this is our parameter space. Case 1, Mach number 0.4, blockage ratio 0.2. So we are below the Kantrowitz limit. And as you can expect, this is how the Mach number field looks like. So essentially, the flow is not even choked in the bypass. Maximal Mach number is 0.56, nothing new. Then we increase the Mach number of the pod right above the Kantrowitz limit, and we observe the following. So the flow in the bypass is choked, and then there is, as I said, a normal shock in this diverging part of our de Laval nozzle, so to speak. And finally, if I increase the pod speed even further to 0.2 Mach number 0.8, as I said, the pressure starts accumulating in front of the pod. This changes this ratio of pressure, and therefore we observe the following flow structure. So a overexpanded de Laval nozzle with the flow that is choked in the bypass and then remains supersonic with some oblique shocks. And those three solutions are representative of the whole parameter space. So let's move on to the results concerning the drag. But before that, let me illustrate what I just said. Here we see again the parameter space with several asterisks which correspond to simulation I run, and the color of the asterisk indicates the flow structure. So below the Kantrowitz limit, we see blue asterisks, so subsonic cases. Then the green ones are those with a normal shock, and the red ones further above the Kantrowitz limit where the overexpanded flow structure was observed. And now I'm showing the drag of these simulations. So in this three-dimensional map, Mach number on the x-axis, blockage ratio on y-axis, and the third dimension is the drag. And the first and most important things you need to observe here is these 3 orders of magnitude of difference in the drag from the low subsonic cases to the high supersonic cases. And also you can barely see that there is this kind of a jump somewhere around here. And to better illustrate this, let's consider a fixed blockage ratio of 0.4 and different Mach numbers. And on the left, you see the drag, and on the right, the drag coefficient. But what I want to show you with these 2 plots is the following. So you see there is a first kink where at Mach number 0.4, which corresponds to this point here. So as soon as we overcome the Kantrowitz limit, there is a kink in the drag and also the drag coefficient, and also a second kink at Mach number 0.6, so where the flow structure changes. And this was the discussion concerning the drag, and also the take-home message from this slide is really these 3 orders of magnitude of difference, which motivates at least the investigation of a compressor. What can we gain something with a compressor? But before moving to the second part of the analysis, I have a quick slide on a 3-dimensional case I simulated in order to assess whether 3D effects play a fundamental role or not. Because as I said, I did only 2-dimensional analysis. So I took one 3D case, and to keep it short, I compared the flow structure and some macroscopic quantities, such as the drag or the maximal Mach number, and observed that essentially there is not that big of a difference. And so I concluded that the 3D effects do not really play a fundamental role for this analysis. Okay, so now let's move on to the second part, where I include a compressor in the simulation. And so let me first illustrate you the 2 distinct modeling approaches I implemented to represent a compressor. The first one is very simple. It's a zero thickness model that essentially imposes a pressure jump across a surface or a disk. And as I mentioned earlier, I placed it in this converging part of the compressed section. And this is how the pressure looks like, or the evolution of the pressure looks like along the axis of symmetry here. And you see there is really a sudden jump from one cell to the other. And this is the first modeling approach I used to emulate a compressor. So basically increasing the pressure. And the second one is a little bit more sophisticated, but still relatively simple. So I use source terms, namely a momentum source term and an energy source term. And I place those here in this region. So not in a single cell, but in a region, 2-dimensional region. And in fact, the main difference is that now the absolute pressure, again, the same plot, increases progressively and does not really jump from one value to the other. And also to point out the fact that I coupled those 2 source terms in order to obtain a close to isentropic compression, such as in a real axial compressor. So far, so good. Let's move on to a few considerations regarding the power consumption. And before that, let's consider the forces which act on the simplified pod. So we have the drag, which we can compute from the simulation results as the integral over the surface of the pressure and the wall shear stress. Then we have a contribution of the thrust coming from the compressor. And at steady state, all the remaining force, in order to keep a specific velocity constant, must be provided by the linear induction motor. And those 3 can be computed like with those formulas here. And why are they important? Because they allow us to compute the power consumption. And namely, I consider those 2 power sources, the compressor, of which the power can be computed with this formula. So mass flow times Cp times delta T0. This can be found in books. And the linear induction motor power is simply the thrust, which must be provided times the velocity of the pod. And we need those 2 because with them we can compute the total power consumption of our pod. And here I'm neglecting some things like the electronics and other stuffs. But it should work as a first approximation, so to speak. And so I did the following 3 steps for each tested combination of blockage ratio and Mach number. I perform a simulation without the compressor active. Then I activate the compressor and progressively increase this pressure ratio. And I look at what happens to the total power consumption, if it changes and if there is an optimum somewhere. And I do these 3 steps for all those cases, so all those asterisks again, which are above the Kantrowitz limit. Okay, so let's move on to the results. And in this slide, I'm showing you the effects of a compressor on the flow. So before actually moving on to the consideration regarding the power consumption. So here I'm showing the mass flow through the compressor for a specific case. So blockage ratio 0.72, Mach number 0.6, but the same trend is observed for all of the other cases. So I start by a pressure ratio of 1, meaning the compressor is not active, and then I progressively activate the compressor and increase the pressure ratio, and I observe that the mass flow through the compressor increases. So this is expected. It's the first thing I wanted to check in order to observe or assess whether the 2 modeling approaches were doing the right thing. And you can also see that both of them achieves very similar results. So the blue and the red curve are the 2 modeling approaches, fan interface and sorcerer. And the second quantities that I was interested in, it's the most important one, is this pressure accumulated in front. And as you can see here, again, for the same case as before, but it holds for all these cases, the pressure is actually being reduced by a compressor. So by increasing the compressor pressure ratio. So this is what I just said. Yeah, again, the 2 modeling approaches achieve the same results on the flow. And the same trends are observed for all the tested blockage ratio and Mach numbers. So this concerning the effects of our compressor modeling on the flow. And let's now move on to the power consumption. And so here I'm showing for 2 blockage ratios and different Mach numbers how the normalized total power consumption changes versus the pressure ratio. And we can observe a few things. First of all, the total power consumption can be reduced for most of the cases, like those 3 cases, but not all. And also there is an optimal pressure ratio at which this total power consumption is normalized often. And this allows me to draw the following 2 maps, which are the most important results of the thesis or the final results of the thesis. I'm showing again Mach number on the x-axis, blockage ratio on the y-axis. The red line is the Kantrowitz limit. And first I'm showing the optimal gain in total power consumption and below the corresponding optimal pressure ratio. So how did I draw these maps? Let's consider this blue curve here. So blockage ratio 0.72, Mach number 0.4. We see that there is an optimum here in total power consumption. So I'm plotting this gain. So here we can gain 15% approximately of total power consumption. I'm plotting this 15% here. And it occurs when the compressor operates at the pressure ratio of 2. So I'm plotting this 2 here. And this is how you read those 2 maps, essentially. So we can conclude from that the total power consumption can be decreased with a compressor for most of the cases above the Kantrowitz limit. We obtain more benefits further away from the Kantrowitz limit, and also that the optimal pressure ratio increases with the distance from the Kantrowitz limit. So, and before moving on to the conclusions, I have a last slide on 2 additional investigations I performed to generalize the results a little bit. So let me just quickly go through it. Essentially, I changed first the tube pressure from 0.1 atmospheres to 0.01 and observed that the normalized total power consumption versus pressure ratio doesn't change, which means that the results I just showed you, or the maps I just showed you, are independent of the tube pressure. So this is the first investigation I did. And the second thing I did was scaling the whole geometry by a factor of 0.5. because remember, for the original investigation, I kept the tube size fixed and I only changed the pod radius. Now I scaled everything and I compared the two models, so the original and the scaled, and again, the total power consumption versus pressure ratio behaves the same, which again means that to some extent, at least, the results are independent of the system size, or that the maps are valid for different tube and pod sizes. And so this brings us to the conclusions. To summarize, I observed 3 distinct flow regimes, subsonic, supersonic with a normal shock, or consistent with the de Laval nozzle theory. Exceeding the Kantrowitz limit leads to a significant increase in the drag of approximately 3 orders of magnitudes. Both modeling approaches achieve the desired effect on the flow, so increasing the mass flow through the compressor and also reducing this pressure accumulated in front. And for most of the cases, above the Kantrowitz limit, the total power consumption can be reduced. And the higher the distance from the Kantrowitz limit, the higher the benefits, and also the corresponding optimal pressure ratio increases with the distance. And finally, the obtained results are valid for different tube pressures and system sizes. So I had a few limitations on this study, obviously. First of all, I used a relatively simple modeling of a compressor. So there was no physical compressor present in the simulations, and which could add, for instance, additional drag or swirl, which I didn't include. It was not possible to validate the results with experimental data or DNS, or which is direct numerical simulations, because they were not available, simply. I didn't set any limit on the power available from either the compressor or the limb, and I also neglected the rails as well as the efficiency of the linear induction motor. And I also tested a relatively small range of pressure ratios. And finally, the outlook. A more detailed CFD analysis of the system is necessary, with particular focus, for instance, on a more realistic compressor modeling, as I just mentioned, or maybe also include a nozzle in the design at the rear part of the pod in order to gain additional thrust. This is also an idea that it's included in the original formulation or in the original alpha paper. Also, optimizing the shape could be one of the next steps. I didn't really put any focus on an optimization of the pod shape. And also maybe focusing on one or few operating conditions instead of investigating the full parameter space could be a good idea. Also to set the necessary requirements for a possible implementation of a compressor. And also, obviously, experiments for validations are required. And in the long term, implementing a real compressor in order to physically assess its performance could be or should be done, actually. And yeah, this concludes my presentation. Now I'm ready for questions, if there are any, or any sort of discussion.
Thank you very much, Maurice. It was very interesting. I think you can leave your screen shared.
Mm-hmm.
Okay, so then, yes, there are a couple of questions. Okay, I'll start with the one with the most upvotes. So the question is, you mentioned that a shock wave is generated if the pod is moving so fast. Is there a way to use that shock wave to generate energy to additionally power the pod?
No, because let me show. I don't think so, actually, because whenever you have a shock, you have a loss. So a normal shock or an oblique shock is always a source of loss in entropy and energy. So actually, ideally, what you want is avoiding shocks in theory, because also a shock increases the drag. So if you're able to avoid shock, the formation of those shocks, you reduce part of the drag. And I don't think there is a way of doing the opposite. So gaining something, you mean like from the tube perspective, like having some kind of device in the tube that captures the shock and creates some kind of energy. I'm not aware of any project or study on that. So I could be wrong, but that's my point on that. I hope this answer, if not, just write in the chat.
It's an interesting idea, actually.
Mm-hmm.
Okay. Then the next question is, how have you managed to model the air at this flow pressure? Do you assume ideal gas?
Yes, it's I assume the ideal gas, and you basically with star CCM you can set everything you want in your domain. So I set the tube. Let me show you. Yeah, I set the tube conditions. Basically, you give which gas you are modeling. I modeled simple air with basic properties. Once you fix the temperature, everything is, or all the properties are fixed. So yeah, it's something it's an input of your simulation essentially.
Okay, thank you. Then the next question is, do you also include turbulent flow, especially on your Laval approach?
Yes, so I didn't mention it, but I used the K epsilon turbulence modeling. This is also something already included in star CCM Plus. I'm not sure how familiar you are, but basically before assessing whether the flow is turbulent or not, you need to check the Reynolds number. And so before doing the simulations, it's something you can compute beforehand, and the Reynolds number was above a certain threshold, which indicates that the flow will be turbulent. So this tells you that in your simulation, you need to select the correct turbulence modeling. And yes, you model turbulence, or you model the turbulent effects in the simulation.
And the next question, you told 3D simulations were not considerably different. How so?
Yeah, I mean, let me pick the slide. So it's not different in or regarding the quantities that are important or relevant for this analysis. In this case, I went relatively quickly through it, but like you see here, the pressure which is accumulated in front between 2D and 3D is relatively similar. We're talking about 2% differences. And so is the drag. And so are the coefficients. So obviously there are some difference. The maximum Mach number is different because in the 3D simulations, I have a different shape. So the Laval nozzle around the pod has a different shape. So it expands from a different area. But the two key quantities which determine actually in the end your power consumption, right? So the drag is one of your most important quantity here. They are similar. So in this sense, I'm not missing a key effect if I do a 2D simulations instead of a 3D simulations. This is what I meant. I hope this answered the question.
Yeah, and the next question is, the Kantrowitz limit also applies for the compressor, right? Is there any case where a compressor is more beneficial than simply reducing pod diameter?
So in which sense? Like the Kantrowitz limit? Let me pick the slide. Mm-hmm. So yes, it's true. I mean, in your Kantrowitz limit, I included I think you mean the hole through the compressor is also subject to the Kantrowitz limit. And in fact, what I meant with saying your pod has a certain blockage ratio, I included the area of this compressed part also in the blockage ratio, so to speak. Let me pick this one solution. So this is the design. So the blockage ratio of this pod is not radius of the pod over radius of the tube, but it's actually also including this hole through the pod. So I'm including already in the definition of blockage ratio this hole. I think this was the question. I'm not sure what you mean by that, actually. Maybe you can type in chat, and because I'm not really sure if I understood it correctly.
All right, I might just click in here. That was the question, yes. And I think you got it right. So it's pretty answered. I just think that the design of the interior is pretty challenging when you have to let the air through the inside, while you can also just decrease the diameter of the pod and let the air go through the sides. You know what I mean?
Yes, yeah, exactly. But then, and it's something I also didn't really consider, you have to consider cost, like, or the other way around, you cannot make your pod as small as possible because you need to carry people. On the other hand, you cannot make your tube as big as possible because it costs more. So I didn't focus on this, if you want, feasibility. I just wanted to give you an overall, like a map which you can read. If you're designing your pod and you say, my pod is this big and I want a tube that is that big, so I am located here in the parameter space, what can we get with a compressor? But yeah, the first question was, I mean, yes, I hope I answered it correctly. So the blockage ratio already includes this hole for the compressor.
Yeah, all right. Thanks for the talk, by the way.
You're welcome.
Good. Thank you very much, Maurice. It was super nice. Thanks for explaining on these questions. Is there any last urgent questions? So please vote it up on the Slido. Time is quite advanced. And we will have some last minutes to also maybe shoot general questions. I saw a question arise from a student who wants to know if there is student thesis also advertised by TUM and Emden Leer. Maybe Levente or Lucas, please, could you give some insights on this? If this is also possible, if German students want to have a chance to work on these topics and then present also in this framework. Please,
yes,
Levente.
Of course.
From our side, yes, it is possible. We have a few chairs and also professors who are trying to support us in this regard. And currently there are also a few open topics for semester, master thesis, or even bachelor thesis. So if someone is interested from the TUM, then feel free to contact me. And hopefully also in the future, we will get even more possibilities to write thesis at the TUM.
Same goes for the University of Applied Science in Leer and University of Oldenburg. So just reach out, whether it's from the study course of engineering physics or any other study course. We have projects or modules with projects in Emden and in Oldenburg, and those go for also for all different kind of studies, so also economics department and so on. So in case there's anybody who wants to have a project, just contact us and we'll arrange that. Or bachelor or master thesis.
Great. I think we will also hear some of these topics presented in the coming seminars. I'm already looking forward to those, ranging from technical but also to non-technical aspects. So if there is no more urgent questions rising up in Slido, Natalie, please let me know if there is. Then I think we can already timely look and watch out for the next session. Natalie, do you know what's up next?
Yes, exactly. I can give a short insight for the talk for the seminar in 2 weeks. First, there was one last question on Slido, and the question was if the seminar is accessible online, if there will be a recording. So yes, the recordings will be uploaded to vacuumtransport.org, where it is linked to YouTube, and you can also find all the previous seminars there. And yes, so for the next time, it's in 2 weeks, because in a week there's a holiday in Switzerland on Monday. Therefore, the next seminar takes place in 2 weeks. So we have 3 talks, one by an industry expert and 2 student talks. And so the industry expert is talking about large-scale testing of Hyperloop technologies. The first student is talking about design of a rail bridging mechanism for high-speed wheel transport. And the third student, the third person is talking about nose design. So yes, it's now exactly 7 p.m. We would like to thank everyone for joining and for attending the seminar tonight. Also, thank you very much, Lucas and Levente. Bobby and I would like to thank you for participating and contributing to the seminar. It's really nice to have you aboard. And also thank you to the audience. And yes, we're looking forward to this semester, exchanging and learning more about Hyperloop technology in Europe. And yes, see you next time and have a good week. Goodbye, everyone.
Thank you very much too. See you next time.
See you.
Thank you. Bye.